Did you know that the 2026 FIFA World Cup is not only the biggest tournament in history, but also the most heavily funded World Cup ever when it comes to two things that seem surprisingly simple: the grass and the ball? But how can pitches in Mexico City, Toronto, and Dallas, despite their completely different climates, elevations, and playing conditions, still deliver nearly the same playing experience? And why is every World Cup match ball equipped with technology capable of tracking hundreds of movements every second? Before the first match even kicks off, FIFA spent nearly 5 years conducting thousands of tests and research projects to standardize virtually every playing condition. Today, join Agriculture Insight as we take you behind the scenes of the 2026 FIFA World Cup to uncover a preparation process that few people have ever seen, where tens of millions of dollars have been invested to create the fairest possible matches for the world's biggest football tournament. Few people know that before rolling onto the 16 stadiums of the 2026 FIFA World Cup, every match ball has already traveled nearly halfway around the world from Sialkot, Pakistan, a city widely known as the football capital of the world. Sialkot produces around 70% of the world's footballs, with many factories manufacturing more than 2 million balls annually and operating at full capacity in the lead-up to every FIFA World Cup. However, among the nearly 1,000 football factories in the city, only a small number are FIFA certified. To manufacture footballs for the world's most prestigious tournaments, these factories must meet some of the strictest quality standards in the sporting goods industry. The process begins with the heart of the ball, the bladder. To create a core capable of maintaining stable air pressure, manufacturers heat butyl rubber and roll it into thin sheets with nearly perfect thickness, because even the slightest variation can alter the ball's pressure and bounce. Next, the rubber sheets are stamped into individual pieces, fitted with an air valve, and sealed together before being placed into a vulcanization mold. Under high temperature and pressure, the rubber polymer chains bond tightly together, forming a completely airtight bladder that is elastic enough to deliver a consistent touch while remaining durable enough to maintain nearly constant air pressure after thousands of high-speed kicks. Once the outer shell has been completed, it is fed through an automated printing system that applies the logo, colors, and graphics to their pre-programmed positions with extremely high precision. Only when every detail is perfectly aligned will the graphics match up seamlessly across the finished ball after assembly. Immediately afterward, the printed material sheets are fed into a precision die-cutting machine, which cuts dozens of identical panels in a single press. For recreational and semi-professional footballs, the panels are stitched together using specialized sewing machines after they have been cut. Skilled workers carefully position the edges of two panels beneath the sewing needle, guiding them by hand so the stitching runs precisely along the seams, gradually transforming individual panel sections into a complete ball. The quality of this process directly affects the ball's roundness and overall stability, so workers must maintain perfectly consistent thread tension throughout every seam. Even a slight misalignment between panels or uneven stitching tension can distort the ball's shape, cause unpredictable bounces, and prevent it from meeting playing standards. However, for professional match balls such as those used in the FIFA World Cup, the panels are no longer stitched together. Instead, they are joined using thermal bonding technology. First, workers apply a specialized adhesive to the edges of each panel before assembling them according to precise engineering diagrams. The entire outer shell is then placed into a thermal bonding mold, where high temperature and pressure fuse the panels into a single seamless structure. Compared with traditionally stitched footballs, this technology creates a nearly seamless surface that offers superior water resistance, better shape retention, and a more stable, accurate flight. It is also the same technology Adidas has used for every official FIFA World Cup match ball since 2006. Before leaving the factory, every football must pass a rigorous inspection process. First, each ball is weighed to ensure it falls within FIFA's official standard of 420 to 445 grams. If the ball is too light, it can be easily affected by the wind. If it is too heavy, it becomes more difficult for players to control and reduces shooting accuracy. Next, the ball is checked for roundness and balance using specialized geometric measuring equipment before undergoing abrasion and rubbing tests to evaluate the durability of the outer surface as well as the color fastness of the printed graphics. But passing the factory's quality checks is only the beginning. To earn the FIFA Quality Pro certification, manufacturers must submit sample balls to FIFA-designated laboratories for independent testing. However, even FIFA Quality Pro certification alone is not enough for a ball to be used at the World Cup. The official match ball of the 2026 FIFA World Cup, the Adidas Tri-Onda Pro, must also meet additional performance requirements set by both Adidas and FIFA. It features a 4-panel thermally bonded construction and connected ball technology with an integrated sensor capable of recording movement approximately 500 times per second and transmitting real-time data to the VAR system to help identify the exact point of contact and support semi-automated offside technology. 16 years after Jabulani, Adidas appears to have solved its biggest challenge, creating a football that is fast enough to make the game exciting, yet stable enough to avoid becoming the center of controversy. So if you had the chance, would you be willing to spend $170 on the official match version? Or would a $30 to $50 replica with the same design be the more sensible choice? Before a single blade of grass is planted for the FIFA World Cup, scientists must solve a remarkably complex challenge. How can 16 stadiums across the United States, Canada, and Mexico, with completely different climates, elevations, sunlight conditions, and stadium designs, still provide players with nearly the same playing experience? FIFA's first requirement is that every pitch must use natural grass. But natural grass doesn't simply mean planting any healthy-looking green turf. A World Cup pitch must withstand 104 matches, thousands of sprints, sharp turns, sliding challenges, tackles, and the harsh summer weather, all without becoming uneven, slippery, or causing the ball to bounce unpredictably. That's why FIFA works with sports turf specialists from the University of Tennessee and Michigan State University, treating every stadium as its own unique engineering challenge. Hot venues such as Miami and Monterey require grass that can tolerate extreme heat and recover quickly from damage. Cooler stadiums, or those with enclosed roofs, need varieties that thrive under limited sunlight. Based on these conditions, the turf system is divided into two primary categories. For warm climate venues, the preferred choice is Bermuda grass. What makes it unique is that it spreads through both above-ground stolons and underground rhizomes. When the surface is damaged by heavy foot traffic, it naturally grows back to repair worn areas, while its underground root system acts like thousands of tiny anchors, firmly securing the sand-based root zone. For cooler venues or stadiums with roofs, FIFA favors a blend of Kentucky bluegrass and perennial ryegrass. Although Kentucky bluegrass does not spread as aggressively as Bermuda grass, its underground rhizomes create a dense, uniform playing surface. Perennial ryegrass, on the other hand, establishes itself extremely quickly, allowing worn sections of the pitch to recover in a short period of time. Together, they help maintain consistent traction and playing quality, even under limited sunlight or in cooler temperatures. However, Before a grass variety can be selected, it must first pass an extremely rigorous screening process, much like national teams competing in the World Cup qualifiers. The Flex device, developed by the University of Tennessee in collaboration with FIFA, has become the gold standard for standardizing pitch quality. Beneath its steel casing, the machine's most important component is an actual soccer cleat mounted to a mechanical arm. During testing, the arm forcefully drives the cleat into the turf and twists it, accurately replicating the movement of a 76-kilogram player, the average weight of a professional footballer. Sensors then record every response from the playing surface, allowing experts to directly measure its firmness, stability, and traction. The device isn't used only before the tournament. It is also deployed directly in stadiums to perform continuous measurements after every training session and match, monitoring the condition of the grass in real time. This is especially important because 8 World Cup venues that normally use artificial turf have been converted to temporary natural grass. The Flex system is used to determine whether these newly installed natural grass surfaces, laid over specially engineered sand-based foundations, provide the same shock absorption and traction as permanent, natural grass pitches. Only grass varieties that are firm enough, resilient enough, and supported by root systems strong enough to resist tearing or shifting under thousands of players' footsteps are approved for planting. But before reaching the world's top stadiums, every FIFA-approved grass variety must undergo a growing process lasting 12 to 18 months, and in some cases up to 2 or 3 years, at specialized turf farms before becoming a fully mature playing surface. Most of this turf is grown on a layer of sand placed over a specialized plastic membrane, forcing the roots to spread sideways instead of growing deep into the ground and forming a strong, interconnected structure. Throughout this period, every turf field is cared for like a professional athlete, from mowing and irrigation to carefully managed fertilization, ensuring its height, density, and uniformity consistently meet FIFA's rigorous standards. Once the root system has become so densely intertwined that the entire turf remains intact even when lifted, it has reached the ideal stage for harvesting. Before the turf harvester begins its work, workers must first manually wrap the leading edge of the turf around the machine's steel rolling drum to create an initial anchor point. The roller system then automatically controls the tension, winding the entire turf into tightly packed cylinders. With its ultra-thin steel blade gliding just beneath the root zone, the machine cleanly lifts each strip of turf before rolling it into massive big rolls stretching tens of meters in length and weighing up to nearly 1 ton, while preserving the entire root system and the sand-based growing medium beneath it. Once the process is complete, the turf rolls are immediately loaded onto refrigerated trucks where temperature and humidity are carefully controlled to keep them in optimal condition before they become the playing surface for the world's biggest football matches. And now, welcome to the most anticipated stage of the process, transforming an ordinary stadium into a World Cup stage. About 1 month before the opening match, many stadiums in the United States and Canada, especially American football venues that normally use artificial turf, have their existing surface completely removed before the foundation is rebuilt and expanded to meet FIFA's official pitch dimensions of 105 by 68 meters. Once the sand base, drainage system, and playing surface have been precisely leveled using laser-guided equipment, the natural turf rolls are brought into the stadium. A specialized turf-laying machine then slowly unrolls each section into its designated position, while technicians follow behind using rakes and specialized knives to pull the edges tightly together, trim away compressed grass, and remove excess sand so that the seams become almost perfectly invisible. This is one of the most critical stages of the entire process because even a gap of just a few millimeters can alter the ball's path or create a tripping hazard when players accelerate. Completing a FIFA standard pitch typically takes 2 to 5 days for the turf installation alone, depending on the stadium. Once the installation is finished, the entire surface is lightly rolled with a sports roller and evenly irrigated, allowing the roots to establish quickly in the sand beneath and creating a flat, firm, and uniform playing surface before the final stage of turf care begins. However, installing the turf is just the beginning. Over the next 3 to 4 weeks, each turf roll must quickly establish its roots in the sand beneath, allowing all the individual sections to bond into a single, continuous playing surface. To accelerate this process, many stadiums use massive LED grow light rigs, especially those with roofs or high grandstands where large portions of the field receive insufficient natural sunlight. Mounted on wheels, these lighting rigs are continuously moved across the pitch, producing a light spectrum that closely mimics natural sunlight to sustain photosynthesis and stimulate root growth. As a result, within just a few weeks, hundreds of individual turf rolls merge into a single seamless playing surface with nearly identical firmness, traction, and stability across every part of the field. Finally, about 15 to 30 minutes before kickoff, the entire pitch is evenly watered by an automated underground sprinkler system. Many people assume this step is simply to keep the grass greener, but its more important purpose is to standardize playing conditions. A thin layer of water allows the ball to roll faster and more consistently while creating a uniform playing surface, giving players the confidence to accelerate, change direction, and control the ball with the same feel anywhere on the pitch. Just a few minutes later, all of the sprinklers automatically retract beneath the turf, leaving the field ready for the tournament's most thrilling battles. Every time the World Cup takes place, billions of people turn their eyes to the ball, the superstars, and the historic goals. But few realize that the pitch beneath their feet is the result of a massive production process involving a series of complex stages. So how are millions of those artificial grass fibers actually manufactured and turned into the stage where some of football's most iconic moments are written? It all begins with tiny plastic pellets. Under high temperatures and advanced technologies, they are gradually transformed into turf systems capable of withstanding extreme levels of use, from local amateur fields to world-class international stadiums. Right now, let's join Agriculture Insight to explore the entire journey of how these small plastic pellets become the artificial turf surfaces seen on football fields around the world. Few people realize that artificial turf in modern football stadiums actually emerged from a very simple problem. Natural grass cannot grow properly inside enclosed stadiums. As a result, in 1966, the first artificial turf called AstroTurf was installed at the Astrodome in Houston, USA. However, the surface at that time was still quite primitive, hard, rough, and often associated with a higher risk of injury for athletes. Over decades of research and improvement, artificial turf has evolved into its third generation. Today's systems feature softer fibers, shock-absorbing underlayers, and high-speed drainage systems, delivering a playing experience that feels increasingly close to natural grass. This evolution has also driven massive global demand. From community football fields to modern sports complexes, millions of square meters of artificial turf are installed every year. To meet this demand, China has become the world's largest producer of artificial grass. Thanks to abundant raw materials, large-scale industrial machinery, and enormous manufacturing capacity, factories there continuously produce turf rolls that are exported to thousands of football fields across the globe. In other words, before becoming the stage for legendary goals and historic moments, Many of these playing surfaces begin their journey in massive production lines in China. Before the first artificial grass fibers are formed, factories must prepare a large volume of raw materials. Tons of polyethylene and polypropylene plastic pellets are transported to the facility and stored in silos or specialized containment systems. From there, the materials are fed into automated dosing lines, where they are precisely measured before being blended with green color master batch, UV stabilizers, and various other additives. Each component plays a specific role in determining the softness, elasticity, and durability of the final product. Only when all ingredients are mixed in the exact required proportions can the manufacturing process officially begin. Once all raw materials have been prepared and blended in the correct proportions, they are transferred to one of the most critical stages of the production line, fiber extrusion. At this stage, the plastic mixture is fed into an industrial extruder, where a large rotating screw continuously moves, compresses, and heats the material. Under temperatures exceeding 200 degrees Celsius, the plastic pellets gradually melt and transform into a uniform molten mass. When the mixture reaches the optimal state, the molten plastic is forced through specially designed spinnerets containing hundreds of microscopic holes. In an instant, the liquid material begins to form long continuous filaments with precisely controlled dimensions. From a distance, this process closely resembles large-scale noodle production, as hundreds of fibers are created simultaneously and continuously travel along the production line. However, the newly formed plastic fibers are still very soft and easily deformed. To stabilize their structure, they are immediately passed through a water cooling system. After that, the fibers can continue through a series of high-speed stretching rollers. This process not only increases tensile strength, but also enhances elasticity, allowing the turf fibers to withstand millions of footsteps, heavy tackles, and continuous use over many years. In many modern factories, engineers can even adjust the shape of each fiber directly on the production line. Instead of simple flat strands, the fibers can be engineered into C-shaped, U-shaped, or diamond profiles to improve their ability to recover after being compressed. This is also one of the key factors that determines the quality and playing feel of the finished football surface. At this stage, the first artificial grass fibers have taken shape and are ready for the next process. They are guided into an automated winding system, where hundreds of individual strands are gathered and wound onto massive spools, each stretching up to thousands of meters in length. Throughout this process, sensors continuously monitor tension and winding speed to ensure that every fiber is evenly arranged without twisting or breaking. As the finished spools gradually fill the production area, they are transferred to the turf weaving line. Here, technicians select and combine different types of fibers depending on the product design. Some fibers are used to form the main grass layer, while others are designed to mimic younger grass or enhance the natural appearance of the playing surface. Before entering the weaving stage, all fiber rolls must undergo strict inspections for color consistency, thickness, and durability to ensure they meet demanding technical standards. Only then are these fibers ready to be transformed into massive artificial turf carpets. Next, the massive rolls of artificial grass fibers are transferred to the tufting line, the stage that marks the first time the plastic strands begin to take the form of an actual playing surface. Here, the fiber rolls are mounted onto large creels above the machine, while beneath them lies a primary polypropylene backing layer continuously moving through the system. As the machine operates, hundreds of specialized needles move rapidly up and down, punching individual fibers through the backing and locking them into perfectly aligned rows. The entire process is computer-controlled, allowing precise adjustment of pile height, row spacing, and fiber density per square meter. Depending on the design of each type of field, Manufacturers can modify the amount of inserted fibers to create surfaces that are softer, denser, or more durable. As the carpet gradually forms and exits the production line, millions of fibers have been embedded into the backing exactly according to the design layout. However, at this stage, they are still held only by mechanical loops and are not yet strong enough to withstand real-world usage. Therefore, the turf sheet is then transferred to the backing coating stage, where the fibers are permanently locked in place, creating a stable and durable structure for the finished product. After leaving the tufting line, the artificial turf carpets move on to the backing application area, a crucial stage that determines the overall durability of the product. Here, the back of the carpet is coated with a specialized adhesive layer, typically latex or polyurethane. An automated coating system spreads this material evenly across the entire surface, allowing it to penetrate every point where the fibers are anchored into the backing. To ensure uniform adhesion, the carpet continuously passes through material distribution rollers, which maintain a precise coating thickness across the full width of the product. This stage is comparable to laying the foundation of a building, as it permanently locks millions of fibers into the backing layer and prevents them from loosening during use. To help the coating stabilize and achieve full bonding strength, the turf then moves through an industrial heating system. Under carefully controlled heat, the adhesive gradually fuses with the backing layer, forming a solid and durable structure capable of withstanding years of intensive use. By the time it leaves this production stage, the fibers are firmly secured and the turf is ready for the final finishing processes. Once the backing layer has fully set, the artificial turf carpets are transferred to the quality control section. This is the final stage inside the factory before the product is released to the market. Here, technicians together with automated inspection systems evaluate a wide range of critical parameters, including fiber height, fiber density per square meter, color uniformity, and the bonding strength between the fibers and the backing layer. After passing all technical standards, the carpet goes through an automated edge trimming and alignment system to remove any excess material. Next, the massive turf sheets are gradually rolled into large cylinders as the entire carpet is tightly wound around industrial paper or plastic cores. Each roll can reach tens of meters in length and weigh hundreds of kilograms. Before leaving the production line, the turf rolls are wrapped for protection, labeled, and fully marked with technical specifications to support transportation and future installation. From there, they are moved to storage facilities or directly loaded onto trucks, beginning their journey to football field construction sites around the world. When the finished turf rolls arrive at the construction site, the installation process begins. First, the ground is leveled and the base system is prepared to ensure stability for the entire playing surface. Once the foundation meets the required standards, the massive rolls of artificial grass are brought into position and gradually unrolled across the surface. Each roll can be tens of meters long and weigh hundreds of kilograms, so handling and installation require specialized equipment along with experienced technical teams. The turf sheets are laid side by side according to the field design, with careful alignment to ensure that the seams are nearly invisible to the naked eye. Each roll must be stretched and flattened to remove any folds or creases formed during transportation. Although this is only an intermediate stage in the overall process, it plays a crucial role in creating a uniform playing surface before moving on to the final finishing steps. Once all turf sheets have been laid in their correct positions, the installation team begins working on the seams between them. Although the surface may already appear complete from a distance, it is still made up of multiple separate strips of artificial grass. To transform it into a seamless playing field, the edges are precisely trimmed and tightly joined together. A specialized joining tape is placed beneath the seams, followed by the application of industrial adhesive to bond the turf sections into a single unified surface. Workers continuously check the spacing between fiber rows to ensure that the seam becomes virtually invisible when viewed from above. After the adhesive has fully cured and reached the required bonding strength, the entire field surface is firmly secured and ready for the next stage. This step is also critical for the visual quality of the pitch, as any imperfect seam can still be easily detected, even from a distance. Once the seams between the turf sheets have been fully secured, the entire playing surface enters its first finishing stage with a layer of silica sand. This is a crucial step designed to stabilize the structure of the field before it is put into real use. Specialized spreading machines begin moving along fixed lanes, evenly distributing a fine layer of sand across the entire football pitch. As it is applied, the ultrafine grains quickly work their way between the artificial grass fibers, filling the voids within the turf system. This process helps anchor the fiber base, keeping the blades upright and significantly reducing movement or displacement when subjected to strong external forces. Immediately after the silica sand layer has been fully applied, the next step is the installation of recycled rubber granules. These granules are typically produced from shredded used tires, then processed to achieve a uniform size before being used in construction. Specialized spreading machines continue moving across the entire field, distributing the rubber granules evenly between the grass fibers according to the design specification. Unlike the sand layer, which stabilizes the structure, the rubber layer acts as an elastic cushioning system. When players run, accelerate, change direction, or land after physical challenges, this material absorbs a portion of the impact force, helping reduce stress on the knees and ankles while providing a softer and more comfortable playing experience. Once both material layers have been evenly distributed across the entire field, the final step is brushing the turf with specialized machines. These machines are equipped with high-speed, rotating brushes and move continuously across the surface, covering the field section by section. During operation, grass fibers that were flattened during installation and infill application are lifted back upright, restoring a more natural and uniform appearance. At the same time, the brushing action helps the sand and rubber granules settle deeper between the fibers, ensuring an even distribution throughout the pitch. After completion, the surface reaches a stable condition with the right level of elasticity and is ready for final inspection before being put into use. Once the entire surface has been completed with sand, rubber infill, and brushing, the project enters its final inspection stage. Technicians assess key parameters such as surface flatness, infill uniformity, fiber height, and the bonding strength between structural layers. Certain areas are also tested for drainage performance by simulating heavy rainfall over a short period of time. Only when all specifications meet the required standards is the football pitch officially considered complete. From an empty base to a highly engineered surface shaped through multiple complex stages, it is now ready to host professional-level matches. Every year, more than 150 million passports are produced, each embedded with up to 30 of the most advanced security layers available. But their true value does not lie in technology. It lies in the power of the nation behind them. A passport from Singapore or South Korea can unlock access to more than 190 destinations, while Afghanistan remains below 30. The shape is the same, The size is the same, yet the freedom of movement differs by an entire world. In reality, passports are not a modern invention as many people assume. More than 2,500 years ago, Persian kings issued the first letters of passage, but it was only after World War I that passports were standardized into a global border control system. During World War II, June Sugihara wrote more than 2,000 visas by hand, helping around 6,000 Jewish people escape Europe. At that moment, a passport was not just a document, but the line between life and despair. Many people still confuse passports with visas, yet they are two completely different gates. A passport proves who you are to the world, while a visa determines whether you are allowed to enter a country. That is why millions of entry applications are rejected every year. And according to Interpol, more than 232,000 cases of stolen or forged travel documents were detected at international borders in 2023 alone. What about you? Have you ever run into trouble with immigration procedures? The process of creating a passport does not begin at the printing press, but at the design table, where every detail is calculated to reflect national identity while integrating sophisticated layers of security. A modern passport typically consists of three main components: security paper, a polycarbonate data page, and an RFID chip for storing information. From this foundation, design is no longer just an aesthetic element, but becomes the first layer of physical authentication. Each passport is essentially a unique, light signature of its nation, a recognition system that is nearly impossible to replicate. The Belgian passport hides an entire universe of Tintin, the globally famous adventurous reporter from the classic comic series by Hergé, visible only under UV light. Canada's passport illuminates the aurora borealis and the iconic red maple leaf across its pages, while the United States passport stands out with the bald eagle and founding symbols. These seemingly artistic details are, in fact, highly sophisticated optical security features, where national identity is encoded directly into light. But design is only half the story. The rest of the passport begins with its raw materials. Passport paper is not ordinary paper. It is made from security-grade cotton fibers, sometimes blended with linen, the same type of material used in banknote printing. With cotton, the fiber supply mainly comes from the southern United States, where the climate produces long, white, and durable fibers that meet the strict standards required for high-security manufacturing. From these qualified cotton fields, the selection process becomes far more rigorous than in textile production. During harvest season, high-capacity machines can collect over 2,000 kilograms of cotton per hour, but only about 10 to 12% meets the criteria for security paper production. Rotating spindles, fitted with hundreds of small picking heads, continuously pull fibers from the bolls, minimizing impurities directly in the field, before the cotton is quickly compressed into large bales weighing around 200 to 220 kilograms for transport. These harvested cotton bales are transported to staging areas at the factory before officially entering the processing line. Here, a fully automated system begins opening the fibers, breaking apart the tightly compressed masses, while simultaneously removing dry leaves, small twigs, and fine dust through a combination of rotation, vibration, and high-speed compressed air. This process not only cleans the cotton, but also loosens and evens out the fibers, preparing them for the next stages. After that, ginning machines continue separating the seeds from the cotton, retaining only the purest fibers, the core raw material for the entire textile industry that follows. If the US dollar is known for its 75 to 25 ratio of cotton to linen, passport paper also uses these two fibers, but the exact ratio is kept confidential. Alongside cotton, linen fibers are added to enhance strength, stability, and resistance to twisting in each page. In farming regions of the northern United States, flax is harvested using specialized pulling machines that extract the entire plant from the ground rather than cutting it, preserving the full fiber length, an essential factor that determines the toughness and durability of each passport page. The nearly 1 meter long flax stalks are then laid out in parallel rows across the fields and left to dry naturally for several weeks to reach a stable fiber state. Once they achieve the required level of maturity, they are gathered by machines and rolled into large bales weighing around 300 kilograms, ready for the next stage in the security paper production process. After that, the flax is crushed, combed, and refined before being blended with cotton pulp. This combination creates a type of paper that is soft enough for printing, yet strong enough to carry a person's identity through hundreds of inspections without structural degradation. As soon as the raw cotton and flax bales arrive at the factory, the journey to create one of the world's most powerful base papers begins, where everything familiar immediately becomes something entirely different. The fibers are cleaned and then mixed into large vats, forming a slurry similar to thin porridge, where thousands of microscopic security fibers, just a few millimeters long, along with invisible identifiers, are deeply embedded into the material's structure. From there, the mixture is continuously spread onto a sheet-forming system, pressed down to a thickness of only about 90 to 120 micrometers, and then dried under strictly controlled conditions before being rolled into large sheets. Everything is then wound into reels and transferred to secure printing facilities. This type of paper never appears on the civilian market and is regulated as strictly as national currency. In many countries, the unauthorized production or possession of this material can lead to criminal prosecution. Once the base layer is complete, the printing stage truly begins, where every detail is transformed into a national fingerprint. Aluminum plates coated with ultra-sensitive carbon layers are engraved with micrometer-level precision, storing the entire design in a form that the naked eye cannot fully perceive. The excess carbon is then removed using specialized rollers and brushes. The plates are cleaned, dried, and fed into a synchronized multi-station printing line. Here, layers of security inks, blue, red, green, and black, are overlaid using offset and intaglio printing technologies, with each layer carrying a specific visual element and anti-counterfeiting function. As the multi-layer security paper passes through, rubber rollers transfer the colors onto the surface with a tolerance of less than 0.01 millimeters, forcing every detail to align perfectly. Even the slightest misalignment would render the pattern incomplete and impossible to replicate without every single layer. Under ultraviolet light, 6mm security fibers begin to glow, confirming that this is no longer ordinary printed paper, but a passport page in the making, where identity is encoded directly into the material itself. But a passport does not stop at paper, because its core lies in the polycarbonate data page, where the chip is integrated from the very beginning, an electronic brain that does not yet carry an identity. This chip is essentially a tiny RFID microchip, capable of storing and transmitting data contactlessly when passing through control gates. Inside, it is designed to hold biometric images, personal information, and encrypted security keys. But at this stage, it has not yet been activated or encoded. The entire system only truly awakens during the personalization process, transforming it into an inseparable part of a person's digital identity. Once the data page has the chip embedded, all components move into the booklet assembly line. Specialized stitching and pressing systems secure each page with extremely high precision, while the spine is creased using a specially designed blunt blade to shape the structure without damaging the internal security layers. At this stage, the passport is physically complete, but it still does not belong to anyone. Immediately after that comes the most critical step, the one that transforms an anonymous passport into a legally valid identity: personalization. Before this stage, each citizen's biometric data has already been collected and verified within the system. Only then does personalization officially begin. The portrait, ID number, and all personal information are laser engraved directly into the multi-layer polycarbonate structure. When the laser interacts with the material, it alters its color at a microscopic level, producing extremely high-resolution images that are nearly impossible to modify or counterfeit, the moment an anonymous passport officially becomes a citizen's legal identity. After personalization is complete, each passport must undergo strict security checks, including RFID chip readability, data accuracy, and the response of security inks under UV light. It is then registered and activated within the National Identification System, the point at which it officially becomes valid for international use. From that moment on, a passport is no longer just a paper booklet. It becomes a nationally issued identity document that must be protected throughout its entire lifespan. That is why passport covers exist as a simple yet effective armor, from moisture-treated genuine leather to modern materials like polyurethane and waterproof PVC, even incorporating RFID blocking layers to prevent unauthorized data scanning. Thanks to this small layer of protection, a passport can accompany you through hundreds of security checks, carrying your identity across borders worldwide. Few people realize that today's brightly decorated Christmas tree traces its origins back to the ancient forests of Germany, where evergreen trees once stood as a fragile symbol of life amid harsh winters. During the Middle Ages, Christianity adopted this symbol, and by the 19th century, a single photograph of Queen Victoria was enough to transform a local custom into a global Christmas icon. Yet behind the sparkling lights lies a long and demanding production cycle. Each natural Christmas tree takes nearly 9 to 10 years to reach maturity, while growers earn little to no income throughout most of that time. Today, 75 to 80% of American households choose artificial trees. Convenient and fast, but leaving behind plastic waste and a carbon footprint that can last for decades. And to truly understand the choice between natural and artificial trees, we need to return to the very starting line, where Christmas trees begin their lives as tiny seeds. The journey of cultivating a Christmas tree does not begin in the forest, but in a tightly controlled environment where seeds are carefully selected based on maturity and germination potential. They are sown into a specialized growing medium made of peat moss and ground bark, porous enough for roots to breathe, yet moisture retentive to maintain stability. Once the surface is leveled and watered with precision down to each cell, the waiting begins. After 10 to 14 days, the first seedlings emerge. In the weeks that follow, the young trees grow almost silently, focusing their energy on building a strong root system, the foundation that will determine their resilience throughout many years of growth ahead. Once the young trees are strong enough, they leave the enclosed nursery and move into outdoor growing fields, where environmental conditions are managed through large-scale automated irrigation systems. Here, the trees are no longer fully sheltered, but gradually adapt to sunlight, wind, and natural environmental fluctuations. They are organized into plots based on age and growth rate, with water and nutrients continuously adjusted over many months, even years, to prepare them for a stable and sustainable life in plantation forests. After leaving the nursery, young Christmas trees officially enter the stage that will shape their future. Before being planted permanently in the field, each tree is strictly graded based on height, root system health, and growth rate. The soil is carefully plowed into straight, uniform rows, with spacing of approximately 1.8 and 1.8 meters per tree, wide enough for roots to penetrate deeply and for the canopy to develop evenly over time. Planting is carried out continuously, combining machinery with manual labor. Each tree is positioned perfectly upright, its roots placed directly into moist soil, then backfilled and secured immediately. During this early stage, irrigation must be precisely controlled, as even a minor deviation can result in the loss of an entire planting block. As the trees grow, protective netting systems are installed to shield the terminal buds from strong winds and frost, because a single injury to the top shoot is enough to permanently destroy a tree's commercial value.